today we're going to be talking about covalent bonding and covalent nomenclature. So our big idea for today is that covalent bonds form when atoms are sharing electrons. Now last time we talked about when atoms are giving away or taking electrons, and that was ionic bonding. So today covalent is sharing electrons. And a covalent bond is formed between two or more nonmetals when they are sharing those electrons. So we're going to look at a lot of examples today, and you guys are going to learn how to draw a Lewis structure of them. Just to let you know, the molecule is the representative particle of a covalent bond. And remember how we talked about last time, the formula unit was the representative particle of an ionic bond. So now we're talking about molecules, whereas before we were talking about formula units. Before we get into all of our stuff for today, I just want to point out a couple things about our 7 diatomic molecules. And they form when two atoms of the same element share electrons, and they're basically never, ever, ever found alone. So they are often found attached to each other. So you can see this is actually happens to be, this is what you got. Nitrogen, oxygen, all these guys right here, and they actually form 7 on the periodic table plus our hydrogen. So they form a number 7 on the periodic table plus hydrogen. And they're either found paired with each other, or they could be found in other molecules. So Ms. Frankvick's going to show you right now where those are. And you should probably mark on your periodic table.
So it's hydrogen, and then the 7, or the 6 here, that form a 7, starting at atomic number 7. So they start at atomic number 7, which is nitrogen. They form a 7 down to iodine, and in total there's 7 of them. 1, 2, 3, 4, 5, 6, and hydrogen is 7.
So you see that they're often going to be found paired together if they're not in some other sort of molecule. And like nitrogen gas makes up 78% of our atmosphere, and this is the oxygen gas that we need and breathe to live, and it's made during photosynthesis.
Now, it doesn't mean that in all compounds with other atoms, they're always going to be in pairs, right? Like H2O, there's only one oxygen in H2O. It doesn't always have to occur in pairs, only when it's not bonded to any different atoms.
Exactly. So, we also just want to talk to you about our acids, and the best way to identify an acid is if it starts with a hydrogen at the front. And an acid is basically a molecular compound that dissociates, which means dissolves, in water or breaks apart into different ions. And one of those ions is always going to be hydrogen, and that's what it's always going to start with at the beginning. And and then the other part is going to be some other sort of negative ion. So some anion. So we have 2 examples over here, hydrochloric acid and sulfuric acid, and you can see they both start with hydrogen. It's a different number, but that's okay. And they're always going to be in aqueous form. We're going to talk about the state of matter more next semester, but that is telling us that it is dissolved in water. AQ stands for aqueous, and it means dissolved in water. Yep, I think that's it. So I'm just going to quickly go over the different types of covalent bonds, and there's 3 that we have to know about. The first one are single bonds, and that's when one pair of electrons is shared between 2 atoms. So you can see our example is methane, and you can see how carbon and all those hydrogens are each sharing one pair of electrons. Now you can see instead of drawing 2 dots like I would for a normal Lewis dot structure, instead we have a line. So that line, which that note is at the top of the board right there, that line is representing a pair of shared electrons. And it's very different than just drawing a lone pair, which is 2 electrons that aren't being shared by anything. So a double bond is when 2 pairs of electrons are shared, okay? So 2 pairs are shared by the same atom, okay? You can see there's multiple pairs of electrons being shared here, but the difference is here they're both being shared by the same atom. So we were talking about oxygen before as one of our 7 diatomic elements or diatomic molecules, and it actually has a double bond with itself. So that together is sharing 2 sets of 2 electrons for all together. And then we have our triple bonds, which are 3 pairs of electrons being shared, and nitrogen, our other special diatomic molecule, is an example of that. So you can see all together nitrogen is sharing 6 electrons between 2 different atoms. Now, something that's important about double and triple bonds is A, we're not making you predict them, so that's exciting for you, and B, they're only formed either with carbon or with diatomics of oxygen and nitrogen like we demonstrated here. So these are the only times you're going to see it, or if carbon is formed bond with some other atom. And then when you see that, you are going to have to put in our lone pairs, and Ms. Frankovic's going to teach you how to do that in just a second. We need that board. Good.
All right, so we've drawn the Lewis structures for ionic bonds. We're now going to draw the Lewis structure for covalent bonds, or for molecules. Our steps that we're going to use, the first part is the same. We're still following the octet rule, right? All of our atoms want to be like a noble gas. They want a full 8 valence electrons. So keep that in mind as we're doing this. The first step is we're going to count the valence electrons. And we've done this for you in our first example down here. We've counted the valence electrons. We have nitrogen. We have 1 nitrogen. Each nitrogen has 5 valence electrons, which you should be able to predict from the periodic table, which is a total of 5 electrons for nitrogen, 5 valence electrons. For our hydrogens, there's 3 hydrogens in NH3. Each hydrogen has 1 valence electron for a total of 3 electrons. When you add those together, you get a total of 8 valence electrons. We need to make sure that when we're drawing our Lewis structures, we have those 8 valence represented at the end of our structure. So the next step is you're going to draw the Lewis dot structures for each atom, which we've done down here. Right?
Just like you would do for our ionic bonding.
Right.
Same first step.
Right.
Or second step.
We're then going to use arrows to complete electron pairs. So remember that 2 electrons, they're sharing electrons in 1 bond. So we draw that as a line. So these arrows are going to be similar to this bond. Arrows complete the electron pairs. So each hydrogen has a lone electron, and it's going to bond with each of nitrogen's lone electrons. So Ms. Thomas is drawing the arrows there. The central atom is either going to be carbon or it's going to be a lone atom. So if you see one atom like nitrogen, the only nitrogen there with 3 hydrogens, that's going to be the atom that's in the center of our molecule that we're drawing. The next step is that free non-bonded electrons are going to remain as lone pairs. So you see nitrogen has 2 unbonded electrons. So Ms. Thomas is going to draw those 2 unbonded electrons to the right of nitrogen. All right, so there they are. They're still non-bonded, okay? Just like they are here, they're non-bonded. They're lone pair. And then the last step is to draw the revised actual Lewis structure, which she just did here, right? Instead of arrows, we're actually using our bonding lines. And then we need to count the total electrons. Do they add up to how many valence electrons we said were there? So they should add up to 8. Remember, each line counts as 2 electrons. So we have 2, 4, 6, and this lone pair is 8, which is our number that we're going for.
I do want to say one thing, that when we were doing this, we are just completing the octet rule again for everyone, which is what we did for ionic too. But remember, they're just sharing electrons instead of exchanging them. Hydrogen is a bit of the exception because remember, it only has a sublevel that can fit 2 electrons, so it is happy in a noble gas. It has a noble gas-like configuration and it is stable. So this would be showing also that we've completed our octet rule, right?
So let's add octet rule except for hydrogen. Just 1 bond for hydrogen.
Because hydrogen's only going to ever have room for 2 electrons in its electron cloud.
Now our second example, we're going to do the first step the same. We're going to count the valence electrons. So this is CO2 that we're looking at. We have 1 carbon. Each carbon, look on the periodic table, has 4 valence electrons. That gives us a total of 4 so far. We have 2 oxygens. Each oxygen has 6 valence electrons for a total of 12. 12 plus 4, we're looking for 16 valence electrons. Okay. Now, if double or triple bonds are present in the structure, we will give you the structure, okay? So that's why this is already drawn for you. There's double bonds present. We're not going to make you predict that. So all you have to do, down here it says in the corner, is add in the electrons. So we have 16 electrons we need to show. How many are we showing so far? 2, 4, 6, 8. We need to add in 8 electrons. So add 8 electrons. Where are we going to add them? Carbon already feels like it has 8 valence electrons. 2, 4, 6, 8 electrons that it's sharing. So it's happy. The oxygens are not happy. They feel like they have 4 valence electrons because they're sharing 4, each of them. So we need to add in a total of 8. We're going to add them as lone pairs, right? When we add in electrons, we're always adding them in as pairs. So I have 1 lone pair, 2 lone pairs. This oxygen now feels like it has 2, 4, 6, 8 electrons. It's happy. Same thing over here. We've added in now 8 electrons. My carbon's happy. My oxygens are happy. They all feel like they have a full octet. I'm adding the electrons kind of diagonally because electrons are going to repulse each other. So we're just drawing them so that they're as far apart as possible from these and from each other, right? These are Lewis structures. We're going to take a look now at how we name our molecules. Just like we did for ionic bonds, we're going to name our covalent bonds, right? So here's our nomenclature. Our rules here, the first rule is the same exact as naming ionic bonds. When we're naming molecules, the first element, the name stays the same, all right? So just like in an ionic bond, the metal stays the same. The first element here, the name stays the same. The second element, the ending is going to change to "ide," which will be the stem plus "ide." Very similar to ionic bonds, right? Our non-metal, like fluorine, we would change to fluoride. Similar here, okay? The big difference is that with covalent compounds, we're adding prefixes. Now, these are going to indicate the number of each atom, okay? So, if we look over here at our table, and this is on the back of your periodic table as well, the number of atoms will be demonstrated by the prefix. I'll hold it up if you read them.
Oh, okay. Okay, and
So right
when we
here.
have those prefixes, we are actually going to drop A or O at the end of them if we are using oxygen, and then only use the O for the oxide part of it. So we have the prefixes on the back of the periodic table, so instead of something monoxide, we would say monoxide for one, and then would be dioxide, trioxide, and then if we go all the way down here, hexoxide instead of hexaoxide.
Right? So if we have 6 of an atom, the prefix on it is going to be hexa. If we have 4 of an atom, the prefix will be tetra. All right? The other big difference with ionic compounds is for covalent compounds, we never reduce the formulas. All right? So ionic compounds, we reduce if we could. We don't reduce here because the prefixes are telling us exactly how many of each atom we have. We have 2 exceptions. The first one is water, H2O, and the second is NH3, which is ammonia. Those do not follow our naming sequence here, but they are covalent compounds. Covalent compounds, all right, they're going to be between non-metals, all right? So,
I just want to add, and remember, our prefixes that we use them before both our first element and our second element. But if our first element and there's only one, we don't have to include mono. So that is right here. So we're going to show an example of that down here, but I just want to point that out. That is really important that we drop the mono at the beginning. We never start out with mono.
All right, so for N2O, we see that N is nitrogen, all right? So we keep the name the same. We're going to add the prefix for this 2. So prefix for 2 is di. So this is dinitrogen. The second element, remember, we're going to drop the ending and add "ide." So this would be oxide. But how many oxygens do we have? Just 1. We have to add that prefix. So this is monoxide. Now, remember, we're dropping, where is it? The O, A or O at the end of a prefix before oxygen. This is not monooxide. It is monoxide, okay? So dinitrogen, 2 nitrogens, monoxide, 1 oxygen. Did I say that right? I think so.
Yeah.
The second example, SiS2. Si, we're just keeping, the name stays the same, all right? So this is silicon. Now, we don't need mono on the first element. So even though there's only 1 silicon, it's the first element, so we don't use mono. So this is silicon, not monosilicon.
And the way I remember that is because we also don't need a 1 at the bottom. So that's what I usually tell my class is that's how you can remember to drop the mono for the first.
And S2, we drop the ending and add "ide." So this is sulfide, but we have 2 of them, so it's disulfide. Silicon disulfide.